Hello students, my name is Shashank Shekhar and today is the 8th day of the chapter, that is chemical kinetics. Okay, so so far we have covered all these facts like our rate of reaction. So if you look at the syllabus here of the chemical kinetics, so we have covered up till this part here. So today we will be mainly focusing on this part, which is the effect of temperature, which mainly tells about the effect of temperature on the rate of reaction. Concerning about this part, that is the concept of collision theory. So we'll look at it tomorrow. In the next lecture, we'll see it in the next lecture. So let us start our today's class. So if I look at the topics that are to be covered, so that topics would be the temperature dependence. So when I said that, okay, this thing is rate of reaction is dependent on temperature. So what do I mean by this? In what sense or in what way this rate of reaction is dependent upon temperature? So we'll see a qualitative analysis of this. Further, all the slides will be covering the quantitative analysis, which is mainly handled by this Arrhenius equation. Okay, which is mainly handled by this Arrhenius equation. Next, we'll see the activated complex theory, which is based upon this Arrhenius equation only. It was given by Arrhenius only. So we'll see this. Also, we'll see what is reaction profile. So it is very important to study about this reaction profile. What is reaction profile? Then, what is Boltzmann plot? So this Boltzmann plot is basically dealing with the temperature dependence of the molecule's energy. Okay, so we'll see it. Further, we will see the effect of temperature on the Boltzmann plot. At last, we will study about this Arrhenius plot. What is this Arrhenius plot? Means whenever we have an equation, we will always have a plot related to it. So we'll see that plot also. At last, we'll see what is Arrhenius equation, which is at two different temperatures. So it is the most important part of this formula. So when we define it for two different temperature and we find out what is the ratio that is connecting both of these. So that are the topics which I will cover today. So let us start our class. So first of all, what is temperature dependence? What do I mean when I say temperature dependence? Okay, so what do I mean when I say temperature dependence? So for those who are aware about this temperature effect, must have observed or must have heard also that that if we increase the temperature, then the rate of chemical reaction generally increases. I'm using the word generally here because some of the reactions are not accelerated, they are deaccelerated by increasing the temperature. Like the ones are your exothermic reaction, I would say. So the exothermic reaction are not accelerated, instead they are deaccelerated in the backward direction. Yes, I would say that they are accelerated but in the reverse direction. So this is clear. Now next I will say about an illustration in which we have decomposition of N2O5. So you will see how drastic change this temperature has on the time that is taken by the reaction to complete or on the reaction rate. So we have taken three different temperature: 50 degrees Celsius, 25 degrees Celsius and 0 degrees Celsius. Now if you see here that we have decreased the temperature by half. 50 minus 25 is equals to 25. So we have decreased it by half. So you can see that time has increased almost here. 12 5 is 60 and 6 5 is 30 times. Okay, so you can see what a drastic change has been seen. So on doubling the temperature, you are multiplying the time taken by a factor of 5. So this is a very large change. Similarly, if we move from this 25 degrees Celsius to a much lower temperature, that is 0 degrees Celsius, so we are decreasing it by 15 I would guess, then this time is going from 5 hours to 10 days. Okay, so this is quite a very good illustration of how this temperature changes the rate of reaction. So three samples are there. 50 degrees Celsius, 12 minutes. Good. 25 degrees Celsius, 5 hours. 0 degrees Celsius, it results in 10 days. So see how fast this time is increasing or how fast the rate of reaction is decreasing upon changing the temperature. And also this rate constant that we have seen often, it is also a equilibrium constant. Means it is ratio of two equilibrium constant, it is kf by kb. So it is also an equilibrium constant, right? Now if I talk about another example, so that is mixture of potassium permanganate and oxalic acid. So you must have seen that potassium permanganate has a violet color. Now if we dissolve this potassium permanganate in oxalic acid, it decolorish due to reaction. Now what happens to increase in temperature, that at higher temperature this decolorization is seen very faster. So what we are doing is we are taking physical examples, physical changes, because to see molecular changes it's very difficult. So what we are doing is we are observing those reactions which have a physical change, like this color you say, or the state, or whether we have this aroma. So by observing these things, we can easily predict that how temperature is affecting the rate of reaction. So here it is written that at a higher temperature, it decolors faster than compared to lower temperature. So it implies that, okay, the increase in temperature, both of the example implies that increase in temperature increases the rate of reaction and vice versa. Okay, this is clear. Now a very good quantitative analysis have been made and is seen that if we rise the temperature by 10 degrees Celsius, then the rate constant is nearly doubled. Okay, this is a very good you can say estimation for almost all of the reaction. It says that if we raise the temperature by 10 degrees Celsius, then the rate constant doubles. So if we suppose we go from here to here, so if you can see here that if I increase the temperature from say 10 degrees Celsius to 20 degrees Celsius, then suppose 8 was the rate of reaction, 8 m per second. So that would now become 16 m per second. So this statement means this formulation, that upon rising the temperature or rising the temperature by of 10 degrees Celsius would increase the rate constant to nearly double of its original value. Now this 10 degrees Celsius is not for only Celsius. If you increase for Kelvin also, then also it will be doubled, because this change in case of temperature is same throughout all units. So this means you must know that if two temperatures have a difference of say 3 degrees Celsius, then they will also have a difference of 3 Kelvin. So if you convert both those you can say values into Kelvin, then you will also get you will still get the same say difference. This is clear. So if we increase either by 10 degrees Celsius or 10 Kelvin or 10 Fahrenheit, they will get the same rate constant increase, that is doubling of the rate constant. So this is a kind of temperature dependence of the rate of reaction. So this I mean this by the dependence means how the temperature is changing the reaction. It is doubling the rate of reaction by increasing the temperature by 10 units Kelvin, simply 10 unit temperature. Okay, so this is about the temperature dependence. Now next is the most important one, that is the Arrhenius equation. So what did Arrhenius do? He formulated a formula, very good formula I would say, that directly relates the rate constant with temperature. Okay, the rate constant with temperature, and since rate is directly proportional to rate constant in some sense. Okay, so initially we were taking rate constant as constant, but it is variable when we take different temperature. So upon taking different temperature, we found that it varies in this way. This rate constant varies in this way. And if the rate constant will increase upon increasing the temperature, then of course the rate will also increase. Now, how is this increasing? So do not get hyped by how we will analyze this upon increasing what will happen to K. Just simply go step by step. First, take this. This is T. So first we will increase T. So what will happen to this overall in excluding negative sign? This overall value, that is EA by R, T will go down because this T is present in the denominator. Now if we include, this will go down means it will reduce, it will get reduced. Now if we are removing the negative sign, this value is increasing. If we include the negative sign, then this value will increase. Now since this thing is a power of E, so if it is power, so then also it will increase. And since E is not a fraction or a decimal, it is a number that is greater than 1, so raising the power will always increase its value, Now since this value is wholly is increasing, therefore this value will also increase. Clear? Now what is K? K is given as A multiplied by this value. So if you multiply it by any greater number, then it would also increase, means this whole value is increasing. And hence we can say that, okay, this K is also increasing. So from here, we go on, we moved here to here to here, and we finally found that, okay, we are increasing the rate constant by increasing the temperature. And since this rate is given by R is equals to Ka to the power something, that is order, and rate is directly proportional to this rate constant. Therefore, on increasing temperature, this rate constant is increasing, and hence the rate of reaction will also increase. Now, if I tell you about what are these terms that are here, I will not tell you about this activation energy. We will talk about it later. You know this value earlier only. This universal gas constant. We have temperature. We have A. This is called as pre-exponential factor or frequency factor. So this will remain same for two different temperature. You should remember this, that this would remain same at two different temperature. Further, we have this K, which is rate constant. So this is the overall Arrhenius equation. So it is very important that you get a grasp of it. What is Arrhenius equation? Because this equation is only the basis of finding the relation between temperature and say rate constant, and hence the rate of reaction. So if you recall the back lectures, you will remember that we have seen the dependence of concentration on this rate of reaction and how with the help of rate law. Now we are seeing the dependence of your rate of reaction on temperature with the help of Arrhenius equation. The last one which is left is effect of catalyst. You will also see that with the help of your activation energy plot. Okay, so when we will plot this activation energy, you will see that how this catalyst is changing the rate of reaction, or in simple words, it is increasing the rate of reaction. So is this clear to all of you? Okay, we are done with Arrhenius equation. Now we will simplify it further, because this is not the final form, and I would say not the most useful form. The most useful form will be discovered in the later lectures. Okay, the most useful form will be discovered in the later lectures. Before moving to that, let us get an idea about what is activation energy. So this can be understood by understanding this activated complex theory. So it is given by Arrhenius. Okay, so let us try to understand it by using a illustration. So this is the illustration that we have. H2 is reacting with I2, that is hydrogen reacting with iodine and giving 2Hi. So we'll try to analyze it and see how this mechanism goes. So it was proposed by Arrhenius that this reaction goes in this fashion. What does this depict? It says that when a molecule of hydrogen and a molecule of iodine, they combine. When do they combine? When they collide. So upon the collision of this hydrogen molecule and iodine molecule, we get an intermediate which looks like this. Okay, we got an intermediate which looks like this. Now what happens? After some time, this intermediate that is formed, it is formed for a very short span of time, or this intermediate is very short span. Therefore, it quickly goes to your hydrogen iodide. So we get 2 moles of hydrogen iodide from this. So this bond is broken. So I will represent it with a red one. So this bond is broken and we got 2 new bonds. And in this way, we are getting this final product. But what is now activation energy? What is the role of activation energy here? So from going to here, from here to here, we can see that we are breaking bond, and plus we are making bond. But usually this is of higher energy, because in this case, a bond is not made, neither bond is destroyed. So you can see that these are dotted line. These are kind of interaction, but bond is broken always. Okay. Now to break this bond and to make this unstable intermediate, unstable means higher energy simply. To make this higher energy intermediate, we need to have some energy, and that energy is termed as activation energy. So what is activation energy? It is the energy which is required by the reactant during the reaction to go to the intermediate, or to form the intermediate, or the transition state, most accurately transition state. And this intermediate here that we have, this dotted one, is termed as activated complex. What it is termed as? It is termed as activated complex, and the energy which is required to move from 2 hydrogen and 2 iodine one hydrogen molecule and 1 hydrogen iodine molecule to this intermediate is termed as activation energy, and it is represented by EA. And this activated complex is, you can say, denoted by C. This is clear? Okay. So this is our activated complex theory. So we have seen, so if I just revise it all. So first we have seen that this activation energy, this temperature affects the rate of reaction by increasing the rate of reaction, generally if we increase the temperature. Then we have seen the formalization of it, which was Arrhenius equation, that at what extent or in what way does this rate of reaction increases upon increasing the temperature. Then we have seen activated complex theory. So this, since we know that, okay, we have to have this rate of reaction increase upon increasing temperature. So what is this to do with the internal molecule? So basically, we were trying to propose a theory in which we said that, okay, we have to go through an intermediate to get our final product. To go through the intermediate, we need energy, and that energy is supplied more appropriately when we increase the temperature, because it results in thermal energy. Okay, so now we are finding the source of this formation, say increase. So our source is that we require energy to convert our reactant into intermediate, and that energy is given by increase in temperature, that is the thermal energy. Now next thing, so we'll study more about, first of all, this, what is this activation energy. So you must understand this plot very well. So here is a very good plot that I have taken from NCERT, and this graph shows that how the potential energy is varying. How the potential energy is varying upon you can say proceeding of this reaction, upon reaction coordinate increasing. So how does the potential energy varies? So if I talk about the system first of all was, initially the reactant system was first of all was at energy that is equals to ER. Now what we do, we start the reaction. Upon getting the reaction, now this molecule will, or the system will tend to increase its energy to a certain maxima, and the difference between this maxima and the minima is termed as activation energy. And second thing, the species which is present having energy is maximum is termed as activated complex. So it goes up till here. Okay, it goes up till here, and then it falls back here to give the product. And the energy of the product is taken as EP. Energy of the product is taken as EP. Now, if I talk about this specific reaction profile, you can see that the system energy has been decreased from ER to EP. Therefore, it's a kind of exothermic reaction in which the energy is released. And if I talk about what amount of energy is released, we will simply subtract reactant minus product, or product minus reactant. So that would give us enthalpy change. Now we can have another case also if this part was above it. Suppose a graph was formed like this. So in that case, its reaction would have been a endothermic reaction because the final product has greater energy than the starting reactant. So this is clear to all of you. Okay, so this is about reaction profile. Now we will see a more complex example of this reaction profile. So what is difference between that reaction profile and this? The first difference you will notice that we have an extra hump here. Second, we have two transition state, TS1 and TS2. And remember students, this is not a transition state, this is an intermediate. There is a difference between intermediate and transition state. What is the difference? The difference is that a species that is intermediate can be stable for some time, a very small time I would say, but for some time. But it is near to impossible for the independent dependence of this, or you can say independent existence of this transition state. So think of it like this. Suppose you have a ball. Okay, now you push the ball, it goes and reaches here and it just stops. Okay, it goes and just stops here. Suppose this transition state 1 ball, and this transition state 1 ball is in the quite good equilibrium, and a little push, a very little push will either move the transition state to your say intermediate or to your this reactant. So due to this reason, you will see that this transition state is very less stable because only a slight change will disturb the equilibrium. Now suppose the ball comes and stops here for some time. Now if you apply energy, then of course it can go here and there, or thermal energy only, not greater than that, because it is looking like it is very difficult, but once it gets a thermal energy, it will quickly escape here or here, depending upon the nature of reaction. Now what happens, or if it tries to just disturb by a small amount, then since it is a kind of valley, so this will revert back, this ball will revert back here. So just get your analogy with the ball. You are just imagining your ball and energy as same. Now due to this reason, this valley type of this look, this intermediate is more stable because now the ball of the intermediate, I would say the ball of the intermediate will not escape easily, but it's not stable. This energy is very much less, and it will quickly, I would say quickly, not that much quickly as transition state does, but quickly, right? It goes from I to transition state, then further it moves to product B. Okay, now if you remember, you have seen this kind of formations both. If you consider SN1, then it is following this graph, and if you consider SN2, you were following the previous one in which only one transition state was made. Okay, is this clear? Now let us label this all. So the TS1 is the first transition state, the TS2 is the second transition state, the third one is the activation energy, first activation energy, and EA2 is the second activation energy. Sorry, it is the second activation energy. So this is clear for all of you? Okay, so this is all about the reaction profile. You should be well aware about what is reaction profile because it is a quite interesting topic to know about. This is clear? Now next is the Boltzmann plot. Till now we have seen, first of all we have seen that this reaction rate increases upon increasing the temperature. Then we have seen how much it increases or decreases. Then we have seen why does this reaction rate increases. Okay. Now we will see that what is this activation energy, because we know that upon increasing the temperature we increase the thermal energy, which becomes equals to its activation energy, and we get our product. Now how we'll decide that which molecule is having the activation energy and which molecule is not having the activation energy? For this, Boltzmann gave a plot which was basically about the fraction of molecules having energy E. So suppose we take this point, then I would say that suppose this value is 1 by 2, okay, and suppose this is energy is X. So I would say that half of the molecules are having energy X. So this is fraction. This by this I mean fraction. Okay, right. Now this plot was given by Boltzmann and Maxwell. It is called as Boltzmann-Maxwell plot. Now what will happen? According to them, the distribution of this kinetic energy may be described by plotting the fraction of molecules with a given kinetic energy versus any entity with a kinetic energy. So what is Ne by Nt? So this is the ratio of what? The number of molecules having energy E and the total number of molecules. Now next thing, so this is our plot, and this is very important. Now what will happen here? Ne is the number of the molecules having an energy E, and Nt is the total number of molecules. Now the peak of the curve is what is called as most probable kinetic energy, and it is kinetic energy of maximum fraction of molecules. Suppose this point here is the maxima. Okay, this is the maxima. So maxima means if we just try to extrapolate it, you will find that this kinetic energy at this point is owned by the maximum fraction of molecules. Means suppose more than and any other energy, this energy is held by most of the molecules. So you can directly relate with the number of molecules also. So this energy is possessed by the maximum number of molecules. Now as we move to higher kinetic energy, you can see that the number of molecules having this energy is decreasing. Okay, so initially the number of molecules having this much lower energy is less, and upon increasing the energy also the fraction of molecules will decrease. Now this will not touch it. Okay, this will not touch it. This is a very interesting thing to notice. If you are aware about the absolute temperature, you must have observed that absolute temperature is not possible. Now since absolute temperature is not possible, it conversely says that no molecule can have a zero energy. Okay, it conversely says that no molecules can have a zero energy. Therefore the absolute temperature is also not practically possible. Okay, absolute temperature is also not possible. So this you should keep in mind, that it is not that energy which is less will be occupied by the most of molecules, or not that great energy, higher energy that will be occupied. There is certain energy that called as most probable kinetic energy, and it is possessed by most fraction of the molecules or most number of molecules. This is clear? Okay. Now next, what will happen to this plot if we change, or you can say alter the temperature? Now what are we doing? We are increasing the temperature. Here. Suppose we increased it from T plus 10 by factor of T plus 10. Now what will happen to this graph? So you can see 2 or 3 changes from your eyes directly. One more thing, I have marked a barrier here and said that okay, this energy is the minimum energy for the reaction to occur. This is clear? This, since it is kinetic energy graph, so I have marked that this energy is the minimum kinetic energy a molecule should hold so that it could give the reaction. Now if you compare both of this graph, this is lower temperature, this is higher temperature. So you can see that the number of molecules having kinetic energy greater then the activation energy has increased. So this much fraction of molecules have increased which have kinetic energy enough to do reaction. And this is almost double. Okay, this makes the number of molecules almost double. So if we are increasing the temperature 10 times by 10 plus 10, then we are getting an increase in the, say, number of molecules having enough kinetic energy 2 times. Okay, now this is the first thing we observe. Second thing, what do we observe? So if you look here, suppose this is the maxima. You can see the maxima is also moved forward. Means the number of molecules having the most probable kinetic energy has also decreased. So 2 things here. First, the number of molecules having the most probable kinetic energy has decreased because the minima has, you can say, maxima has gone from here to here. Second, the most probable kinetic energy means the kinetic energy that is possessed by most of the molecule has also been increased by some amount. So 3 things are in total happening here. First, the number of molecules having enough energy to participate in the reaction has been increased. Second, the number of molecules having maximum energy, most probable kinetic energy has been decreased by increasing the temperature, and the number of molecules having the most probable kinetic energy has decreased, and the most probable kinetic energy value has also increased. 3 things are this. Now, this is increase in temperature by T plus 10, therefore it is almost doubled. So this is all about the effect of temperature on Boltzmann plots. Now you can see a very clear reference here that as we are increasing the temperature, the number of molecules having enough kinetic energy increase. Now since it has enough kinetic energy, it can react, and it can react, so the rate of reaction will also increase. So this is clear. Okay, now we will move to the next thing, that is Arrhenius plot. So this is our Arrhenius plot. This is our initial equation that we have. So you have seen this equation. Now what do? We take ln on both sides. Now what will happen? Ln k will be equal to ln a e to the power minus ea by rt. So let me define it for you. It's not written here. So upon taking ln, we will get this thing. Now we know that ln a into b is equals to ln a plus ln b. Next thing we know that, okay, this ln e to the power minus ea by rt, this power can come here. So it will come here, and we are left with ln e, and this value is 1. This value is 1. Therefore, we will get our final equation as ln k is equals to ln a minus ea by rt. So if you compare with the equation of straight line, that is y is equals to mx plus c, you will find that y here, y-axis will be given by ln k, x-axis will be given by t. So this is our mx. So x-axis will be given by t, and more appropriately 1 by t. Sorry for the mistake here, the blunder. You should not write, cannot write this. It would be 1 by t. So I will just correct it. So it is mentioned in the graph also. You can see that the y-axis is 1 by t and not t. What is slope? So we have removed this 1 by t, so we are left with minus ea by r. And what about the intercept? So the constant ln a. So this thing is here. So this is not t but t inverse, I would say. So this is clear. So we get a straight line which is having a negative slope and an intercept that is equals to ln a, and the negative slope is minus ea by r. Why a negative slope? Because it is along with a negative sign. So we know that r, which is a gas constant, will be always positive and its value is fixed 8.314. Ea is the activation energy. So it will never happen that the transition state will have a lower energy than the reactant. Then if it is so, then it would go to the intermediate and then will become stable and no further reaction will occur. Therefore, this value will also be positive. So overall this value will be negative. So the slope will be negative and it will fall down like this. Is this clear? Okay. Now let us define the most important aspect of this Arrhenius equation, that is for two different temperatures. So we will take two different temperature and we'll see what is the effect of two different temperature on this Arrhenius equation. So the first temperature is T1. So for T1 we can write the equation as ln K1 minus EA by RT1, and we have assumed that at T1 the value of rate constant is K1. Similarly, at temperature 2 we have assumed that the rate constant value is K2 and the equation becomes this. Now we'll subtract both of these equations and we will get these equations finally. So if I just try to write it more properly, then it can be written as ln K1 is equals to minus EA by RT1 plus ln K2 minus EA by RT2 plus ln. Now you must observe one thing, that ln A values are independent of temperature. Okay, so for both of these temperatures the ln A value remains same. Now if you subtract both of this, you will get it as ln K1 minus ln K2 is equals to minus EA by RT1 minus EA by RT2. Now ln A minus ln B would give us ln A by B, and the previous equation was minus EA by RT1 plus EA by RT2. Further on, just simplifying it, we will take this EA common, EA by R common, and that would give us 1 by T2 minus 1 by T1. Further we can write it as ln K1 by K2 is equals to EA by R. So 1 by T2 minus T1. So we can simplify it, simply cross multiply both of this. So that would give the final equation as this, which is T1 T2 T2 minus T1. Now we have removed this ln factor. So it will become 2.303 log K1 by K2 is equals to EA by R T2 minus T1. Okay, sorry, T1 minus T2 here. T1 minus T2 by T1 T2. Okay, this is clear. Now we'll simply multiply it here and you will get your final equation. So this is just opposite of it, no problem. If you take the ratio opposite, that is K2 by K1, you will get T2 minus T1. If you take it as K1 by K2, you will get it as T1 minus T2. So this is our final equation. Okay, so this is the important part of the equation. So with this, I would end my lecture. To tomorrow, we'll be mainly discussing about the collision theory, which is also based on this factor, that is the Boltzmann plot, but a little bit more advanced. We will just not include the temperature, we will include orientation and all. So we'll look at it. And second thing, we will see the effect of catalyst. What does catalyst does on the reaction profile upon its introduction. So these two things we will see tomorrow. So thank you for today's times. And today is the end of this